What happens when the stars go out? What becomes of the universe when the last light flickers and fades into the abyss? It's a question that has haunted humanity for millennia, a mystery that has sparked both fear and fascination. We gaze up at the night sky filled with the twinkling light of distant suns and wonder about their fate. Each star, a beacon of hope and a symbol of the infinite. We know that stars, like us, have lifespans. They are born in the cosmic nurseries of nebulae, live their lives burning brightly, and eventually meet their end. They are born, they live, and they die. Their life cycles are a testament to the dynamic and ever-changing nature of the universe. But what happens when the last star flickers and fades, leaving behind only darkness? What will the universe look like in the absence of starlight? The universe as we know it is a place of light and energy. It is a vast expanse illuminated by the brilliance of countless stars. Stars are the cosmic furnaces that illuminate the vast expanse of space. They are the engines of creation, forging elements in their fiery cores. They are the building blocks of galaxies, and their light allows us to see and understand the universe around us. Without them, our understanding of the cosmos would be shrouded in darkness. But the universe is also governed by the relentless march of time and the laws of physics. Time, an unstoppable force, dictates the fate of all things. Even stars, those seemingly eternal beacons, are not immune to this cosmic dance. Over eons, stars exhaust their nuclear fuel, a process that seals their fate. Over eons, stars exhaust their nuclear fuel. The outward pressure from their cores, fueled by the fusion of hydrogen into helium, begins to wane. The outward pressure from their cores, fueled by the fusion of hydrogen into helium, begins to wane. This delicate balance is disrupted, leading to their inevitable decline. Gravity, always present, starts to win the battle. The star collapses under its own weight, a process that can lead to different outcomes depending on its mass. For many stars, this leads to a spectacular demise, a supernova that briefly outshines entire galaxies. This cataclysmic event spreads elements across the cosmos, seeding future generations of stars. But for others, the end is quieter, a slow fade into a different kind of existence. These stars quietly transition into a new phase, leaving behind remnants of their former selves. These stellar remnants, the leftover cores of stars not massive enough to go supernova, are called white dwarfs. They are the dense, hot cores left behind after the outer layers have been shed. They are the embers left behind from a cosmic fire, still glowing faintly with the residual heat of their former glory. These white dwarfs are a testament to the star's once vibrant life, but their time too is finite. Over billions of years they will cool and fade, their light slowly dimming until it is no more. They are destined to cool and fade, eventually becoming something even stranger and more enigmatic black dwarfs. These cold, dark remnants will be the final stage in the life cycle of a star. These dark relics will be the final witnesses to the era of starlight. In the end, the universe will be a place of darkness, a silent testament to the stars that once shone so brightly. White dwarfs are fascinating objects. They are incredibly dense, packing the mass of our sun into a sphere roughly the size of Earth. Imagine squeezing all the matter that makes up our star into a ball the size of our planet. This extreme density means that a teaspoonful of white dwarf material would weigh several tons. How do these bizarre objects form? It all starts with a star like our sun, a main sequence star. These stars spend billions of years fusing hydrogen into helium in their cores. This process releases the energy that makes them shine. But eventually the hydrogen fuel runs low, and the core begins to contract under its own gravity. This contraction heats the core, causing the outer layers of the star to expand outward, forming a red giant. During this red giant phase, the star can engulf nearby planets. Our sun, in about 5 billion years, will swell into a red giant, likely consuming Mercury and Venus, and possibly even Earth. Eventually, the outer layers of the red giant are blown away into space, forming a beautiful planetary nebula. At the center of this cosmic cloud lies the remnant core, a white dwarf. It is now incredibly hot, with surface temperatures exceeding 100,000 degrees Fahrenheit. But crucially, it is no longer generating energy through fusion. It is a dying ember, slowly cooling down over billions of years. The cooling of a white dwarf is an incredibly slow process, one that stretches across the vast expanse of cosmic time. Imagine a hot coal taken out of a fire, its intense heat radiating outward. It glows bright red at first, then fades to orange, then yellow, and finally a dull red, each stage marking a gradual loss of energy. Eventually it cools completely, becoming indistinguishable from the surrounding ash, a mere shadow of its former self. This cooling process, for a white dwarf, takes not hours or days but billions upon billions of years, a testament to the slow march of time in the universe. As a white dwarf cools, it emits less and less light, its brilliance slowly dimming. It transitions from a bright white to a dimmer yellow, then to a faint red, each color change a step closer to darkness. Eventually, it emits no visible light at all, becoming invisible to even the most powerful telescopes, a ghostly presence in the cosmos. This is the fate that awaits all white dwarfs, a slow fade into blackness, a silent end to their stellar journey. The reason for this slow cooling lies in the nature of the white dwarf itself, a remnant of a once vibrant star. It is composed mostly of carbon and oxygen, the remnants of the fusion processes that once powered the star, now locked in a final stable form. These elements are locked in a crystal lattice, a highly ordered and dense structure making the star incredibly compact. Heat transfer within this structure is incredibly inefficient, slowing the cooling process to a crawl. Think of it like this. Imagine trying to cool down a pot of boiling water by placing it on a block of ice. The process is painstakingly slow. The heat transfer is slow because the ice is a poor conductor of heat, much like the dense material of a white dwarf. Similarly, the dense crystalline structure of a white dwarf makes it a very poor radiator of heat, trapping the warmth inside. This means that the journey from a white dwarf to a black dwarf is an excruciatingly long one, spanning eons. In fact, the universe is not yet old enough for any white dwarfs to have cooled completely into black dwarfs, a process that will take longer than the current age of the universe. They are still in their infancy, glowing faintly in the darkness, reminders of a universe filled with starlight, each one a silent witness to the passage of time. The eventual transition of all white dwarfs into black dwarfs has profound implications for the future of the universe. It paints a picture of a cosmos that is slowly but surely winding down, a universe where the lights are going out one by one. Imagine a time, trillions upon trillions of years in the future, when all the stars in the universe have exhausted their fuel and died. The last supernova will have long since faded, and the only stellar remnants will be these cold, dark objects scattered across the unimaginable vastness of space. In this era of black dwarfs, the universe will be a very different place. It will be a realm of darkness and silence, devoid of the starlight that illuminates our night sky today. Galaxies, once ablaze with the light of billions of stars, will be populated by these invisible remnants, their presence only detectable by their gravitational pull. The cosmic background radiation, the faint afterglow of the Big Bang, will have faded to near absolute zero. The universe will have reached a state of maximum entropy, where everything is evenly distributed and there are no more energy gradients to drive change or complexity. It will be a cold, dark, and silent place. The prospect of a universe filled with black dwarfs raises profound philosophical questions about our place in the cosmos. In a universe devoid of starlight, what will become of life as we know it? Will intelligence still exist? Or will it be snuffed out along with the last flickering stars? The vastness of space and the immense timescales involved can feel overwhelming, even daunting. It's a stark reminder of the impermanence of everything we know and love. The stars we see today, the very atoms that make up our bodies, will one day be scattered across the cosmos, their energy dissipated into the void. Yet there is a certain beauty in this cosmic cycle of birth, death, and rebirth. The atoms that make up our bodies were once forged in the cores of stars. We are literally stardust, connected to the universe in a profound and intimate way. Even in the darkness, there is a glimmer of hope. The laws of physics, as we understand them, allow for the possibility of other universes, perhaps born from the ashes of our own. While our universe may be destined for a cold and dark future, it is but one chapter in a much larger cosmic story, a story that we are only just beginning to comprehend. The journey from white dwarf to black dwarf is a powerful reminder of the transient nature of the universe. This transformation, spanning billions of years, is a testament to the ever-changing and dynamic cosmos we inhabit. Stars, like us, are born, they live, and they die. Their life cycles, though vastly longer than our own, mirror the ephemeral nature of existence. But their deaths pave the way for new beginnings. The explosive end of a star, a supernova, scatters essential elements across the cosmos, seeding the birth of new celestial bodies. The material they eject into space during their lifetimes, enriched with the elements forged in their cores, will eventually coalesce to form new stars and planets. These elements like carbon and oxygen are the building blocks of life itself. In this sense, the universe is engaged in a continuous cycle of death and rebirth. This cosmic cycle ensures that the universe remains vibrant and ever-evolving. The black dwarfs of the far future, though dark and cold, may still play a role in this cosmic dance. Their presence, though seemingly inert, could influence the gravitational landscape of the universe. Their immense gravity could act as seeds for the formation of new structures, perhaps even new universes. The potential for these remnants to spark new cosmic phenomena is a tantalizing mystery. As we contemplate the fate of white dwarfs and the eventual darkness that awaits our universe, we are reminded of our own mortality. The universe's grand timeline puts our brief existence into perspective. We are but fleeting sparks of consciousness in the grand scheme of things. Yet our awareness and curiosity make our short lives profoundly meaningful. But even in our brief time here, we have the incredible opportunity to explore the cosmos, to unravel its mysteries, and to marvel at its beauty. Our quest for knowledge drives us to look beyond our planet and into the vast expanse of space. The universe is a vast and awe-inspiring place full of wonder and mystery. Each discovery we make adds to the tapestry of our understanding. And while the stars may one day fade away, the human spirit, our thirst for knowledge, and our capacity for awe will endure. Our legacy will be the questions we asked and the answers we sought. For as long as we continue to ask questions, to explore, and to dream, the light of discovery will never truly be extinguished. Our journey through the cosmos is just beginning, and the possibilities are endless.